Okay. Um, Good day, everybody. I'll try to present a relatively brief review of fast radio bursts. Now it's a very wide topic, and 1 hour definitely is not enough. So mainly I'll try to focus on some observational results. However, I'm not an observer. But in the second half, I'll come to the question of the most popular hypothesis at the present moment, which are proposed and which are developing by several groups of authors in order to explain this enigmatic phenomena, which is still unexplored, so unexplained. So actually, we don't know what are fast radio bursts. So at first, I just want to remind you that, as you know, there are many types of different radio transients on the sky related to different types of astrophysical objects. So in this plot, on the vertical axis, there is luminosity, and on the horizontal axis, more or less, it's the duration of the signal. And the blue area, the blue triangle on the right, on the bottom right, corresponds to sources in which it is possible to generate this emission in using some incoherent mechanisms. And in the white area, only coherent emission is possible. And we see that the brightness temperature is very high in the left, the main part of the plot. And we see that fast radio bursts are much shifted from all other types of sources, so they are really peculiar. They are very short, however, not say record short. There are nanoshots from the Crab pulsar, for example, but with this short duration, they are very powerful, and so they look different from many types of other radio transients. So the first fast radio burst was detected in, actually it was detected in 2001, but the paper appeared in 2007. And at that time, it was the only source, the only event, and it was absolutely enigmatic. So it looks something like something very peculiar, and I suspect that many people thought that it can be just an artifact, so maybe it's not something astrophysical. Still, the first source was characterized by a very large dispersion measure, which means that it's very difficult to make it galactic. And in this plot, you can see comparison of the dispersion measure and galactic latitude of FRBs. They are shown with the red circles, and radio pulsars, galactic radio pulsars and radio pulsars in Magellanic Clouds. So we clearly see that typically fast radio bursts are characterized by very large dispersion measure, which is presumably intergalactic. Still, there can be significant contribution from the host galaxy, from an immediate surrounding of the source, but the main contribution might be intergalactic, and in several cases it is more or less confirmed if sources are identified and we know redshift. So let's come back to the first event. It was found occasionally, and it was found by the Parkes telescope, and the event was very bright. So the flux was 3040 Jansky, and it was characterized by a very short duration, smaller than 5 milliseconds. It appeared in a more or less empty region of the sky. There was nothing really peculiar in this direction. So on the left, you can see the Magellanic Cloud, the small one, and the diagram of beams of the Parkes telescope, and one beam is marked by the square, and the source was detected there. So if we try to estimate the radioluminosity simply using the radio flux frequency, we make very simple assumptions about the isotropy of emission. So let's decide that it is very mildly beamed. Then there is just one parameter, distance, and if we take roughly more or less typical intergalactic distance 1 gigaparsec, then we obtain huge luminosity, 10 to 41 ergs. And in the case of the first event, the fluence was not 1, as in this formula, but 30-40 Jansky. So we come to the luminosity close to 10 to 41 just in radio. This is something very peculiar. And of course, the first guess is that you have 10 to 43 ergs per second in radio, then you might have much more in other wavelengths, maybe at high energy. And people tried to search for such counterparts and to propose different models which were related to some powerful events like gamma ray bursts, for example. Gamma ray bursts are good examples in this sense because it looked like the history is repeating. What people discovered at the end of 60s with these spying satellites which were used to control nuclear tests on Earth. People discovered short gamma ray bursts from, say, nowhere. Identification was not possible because position was not determined precisely. And for several decades, people proposed many models to explain cosmic gamma ray bursts. And so with fast radio bursts, the situation is quite similar. Hopefully, we are not going to need 30 years to solve the puzzle of these sources. So the first event was reported in 2007. Then there was a period of doubts because also people found such events which would adopt peritons. It was more or less clear that they are related to something artificial, to something technological, so they are not astrophysical events, but they looked more or less similar to the only fast radio burst known at that time. Also at that time, they were not called fast radio bursts. The term was started to be used since 2013. So the second event was reported only 5 years later, and surprisingly, it was close to the galactic plane. So there were two events, one in the direction more or less towards the small Magellanin cloud, another one towards the galactic plane. So the situation again became very unclear if they are extragalactic or not. But everything changed in 2013 when a paper by Thornton and others appeared in which they reported 4 nuclear cases. And also they started to use the term fast radio bursts. And it can be said that from that moment, 2013, the real history of fast radio bursts began. So all events for a few years were discovered in the archival data. So people tried to find these individual non-repeating short radio bursts in the archives, and it was very difficult to say something about companion transients in other energy ranges. But in May 2014, the first event was identified online, say in real time. And it became possible to trigger programs of observations in this direction. Again, I have to remind that position was not determined very precisely. As we'll see later, typical uncertainty in the area on the sky was like 1 square degree roughly, slightly less maybe. People looked for any transients in this direction, they found nothing. So more or less it was possible to exclude that this particular fast radio burst was related to a supernova or to a gamma ray burst which was pointing towards us. Since that time, many new events have been found in real time, and still we don't have any identification in other energy ranges. So our conference is more or less about multi-messenger astronomy, but here we still have one messenger, only radio waves. Next breakthrough, I would say, appeared when last year results from a new Canadian instrument, CHIME, started to appear. It was very important because this instrument not only can detect a lot of sources, a lot of events, a lot of fast radio bursts, but they can do it at low frequency, because before that mostly sources have been found at classical radio pulsar frequency 1.4 gigahertz. Few have been found at 0.8 gigahertz, but there was nothing at low frequency, only upper limits. And even it was suspected that there is a strong cutoff after, say, 600 megahertz. But CHIME started to present a lot of results at low frequencies. Still, very recently in February appeared an e-print where people tried to search for fast radio bursts at 330 megahertz, and they found nothing. So this is a very strong result, and still it seems that there is a really cutoff somewhere slightly below 400 megahertz. But despite this, spectra of these events are not very well constrained, I would say. So now there is a catalog, and the URL is very simple. It's FRBcat.org. And at the moment, there are actually 110 sources. I didn't correct it here. I tested yesterday. There is one more now. And despite we know just 100 events, plus many events from repeating sources, which we'll discuss later, we can estimate the rate, which is about several thousand events per day per whole sky. So these events might be very typical, so we cannot link them to something very rare, very peculiar in the universe. They might be related to some typical numerous sources. Still, the puzzle is not solved, mostly because of poor localization of sources. So this is again a plot of beams of the Parkes telescope. The radius of each beam is few arc minutes. So more or less this picture is about the size of the moon in the sky, and this more or less represents typical uncertainty in the localization of source using different instruments for non-repeating sources. Very few instruments which are interferometers can obtain much better localization than these few arc minutes. So repeating bursts. The first source which appeared to be repeating fast radio bursts is dubbed FRB 121102. So this means that the first flash from this source was detected on the 2nd of November 2012. The source was found initially by Arecibo, and many repeating bursts also were detected by Arecibo. This is because Arecibo is just large. So at first, repeating sources were too weak, for example, to be detected by Parkes, if it could observe this source. So initially, people reported 10 events, but now there are hundreds of events from this source detected by many, I would say all telescopes in the world working on FRBs, which can observe this source simply due to geographical limitations. So as the source produces relatively frequent bursts, then it was useful to monitor it with several instruments significantly separated from one from another, and so it became possible to obtain very precise localization. So the repeating source, simply because it is repeating, frequently repeating, was the first object for which exact localization was obtained. So localization was very precise. It not only pointed to the galaxy, but even to a small region of active star formation in some faraway dwarf galaxy. So the distance is about 1 gigaparsec, which was a good news because typically people normalize their estimates for this distance, and this was I would say, the final proof that we are dealing with a new class of extragalactic sources. Still, there were some doubts because people said that, okay, this is the only repeating source, and maybe it is extragalactic, but all others didn't show any subsequent flares, and so they still could be something different, but now we don't think that this is a possibility. As there are many events from this source, several hundreds now, maybe even up to 1,000, still such huge number is not reported yet. People looked for counterparts. The first idea was, of course, to look at gamma ray monitors because they easily obtain all sky simultaneously, roughly say. And the Fermi Space Observatory produced very strong upper limits on flares coincident with flares in radio. Then the source was monitored by X-ray observatories by XMM and Chandra. Colored bars represent expositions by these observatories and also by radio telescopes. And these symbols, these dots with lines, they show detected in radio, detected bursts, and there was nothing detected in X-rays. If you are interested in the subject, just today appeared another paper from the team of a Chinese satellite, which is for more than 2 years in orbit now. And also they provide references to all limits from X-ray observations on counterparts of fast radio bursts. Of course, people looked in all possible wavelengths, in all energy ranges, and there are limits from TeV ground-based telescopes. So this is the limit from Veritas. Actually, all instruments MAGIC has provided limits, particularly for this source, because it's very easy to organize joint monitoring with some radio telescope, which presumably can successfully detect bursts during your observations, and then you can really look deep into your data to see if you see something peculiar exactly at the time of detected burst. Of course, the source was monitored in optics, and again without any success. Fermi also provided limits for many FRBs because it provides with a GRP monitor more or less full sky coverage, and there are only limits. So not a single FRB up to now provided a clear counterpart in any wavelength, and it puts very stringent limits on many models of FRBs, and we'll come to it later. Also, people used a little bit different approach. So suppose your favorite hypothesis is that not just an engine of GRB provides simultaneously fast radio bursts, but in a GRB, for example, in a short GRB, due to coalescence of two neutron stars, you form some peculiar object which can be a source of fast radio bursts later on, say years after or days or months after the event. Then it is useful to check it, and people monitored in radio directions towards recent GRBs with known redshift, so we can put real limits on the luminosity of any radio transient, and people detected nothing. Similar approach was used for superluminous supernova remnants. Again, people chose several supernovae of this type during last years and monitored positions of these transients for typically 1 hour with VLA, and again without any result. So again, it provides limits. If we assume that there is no strong beaming, then it's a clear, I would say, indication that remnants of superluminous supernova and remnants of GRBs are not majority of them at least, are sources of fast radio bursts. The same study was done particularly for short gamma ray bursts, simply because we expect that in many cases a very rapidly rotating neutron star is formed after a coalescence of two neutron stars, which is the site for short gamma ray bursts. These are limits from Hess for some particular burst, but observations were not simultaneous. They were made nearly a day after the burst, but still it's interesting to see if people can see something. The answer is no. So for quite a long time, FRB 121102 was the only known repeater, and the second example was provided by CHIME in January last year, and here they presented several repeating events from the same source. As I said, localization is poor, but the dispersion measure is measured very precisely. So if you have rough coincidence in direction and very precise coincidence in the dispersion measure, you can be more or less sure that this is the same source. And so we can speak about repeating source, and we can attribute all subsequent bursts to the source of the original one. The third repeater was presented by a different instrument, by a SCAP, which is Australian SK Pathfinder. And then there was a set of repeaters from CHIME presented in August last year. However, here when they say repeaters, this means that at least there was one repetition. And in this plot for all 8 sources, you can see how many events appeared from each of them. And we see that for several of them, there are 2 or 3 events. So the rate of repeating events can be very different. And for the most productive sources, we know that, especially for the original one, we know that bursts come not randomly distributed. There are periods of activity, and there are periods in which there are no bursts. So there is some periodicity. And really, periodicity was reported for the first time for a different source, not for FRB 121102, but for this one. So now it becomes more difficult to pronounce their names, something like this. So this January CHIME provided the first evidence for periodic activity. This means that as I said, it's not a very precise period between individual bursts. It's more like a period of activity. But for these periods of activity, there is evidence for a relatively stable period, which is about slightly more than 2 weeks, as you see. And this source is localized. Simply because it was simultaneously detected by several instruments, and it's situated in a nearby massive spiral galaxy. So here again we see that sources are related to galaxies with relatively large star formation, but it's not always so. This January, CHIME presented another set of repeaters. I will not stop on it. Let's say a few words about new localization. The second localization was made for a source which is not a repeating one, but it was done by a SCAP, which by itself can make very precise localization. As you see, the localization is about 0.1 arcsecond, and this source was localized in a galaxy with a very moderate, I would say, or even very low star formation, which was puzzling because since the first localization, equilibrium started to shift towards hypotheses which link fast radio bursts with young neutron stars, with young compact objects. And if we're dealing with a massive early type galaxy, then it is still possible. It's not forbidden, but it's much less probable that we can find a young neutron star in such a galaxy. The third localization was made by a third instrument, DSA-10. Again, it's an interferometer. And again, it was a galaxy without strong star formation. Still, star formation is non-negligible. It's about 1/3 of the galactic rate, which is all right. We know that there are young neutron stars in our galaxy. We know magnetars in our galaxy. We know very young supernova remnants and neutron stars inside them. So it doesn't tell you much that the source is in such a galaxy, but still it's important because you know the distance, you know dispersion measure in our galaxy in this direction. You can estimate the dispersion measure in the intergalactic medium, so you can say something about properties of interstellar medium in the proximity of the source, which is also important for modeling. Since maybe not the first event, but very early, people started to discuss that fast radio bursts are very nice instruments for astrophysics because they can be used as probes for different actually subjects, starting from studying of intergalactic medium. And in several cases, despite we don't know the host galaxy of the source, we can localize the source relatively well, and we see that the signal passes through a halo of some galaxy on the way, and it can be used to probe properties of the medium in galactic halo. The first example was presented last autumn, and this year people presented another example, and again from a new instrument in the field of FRBs, from VSRT with aperitif system. And here it was possible to probe halos of galaxies in our local group. The fourth and the last up to now precise localization was made for this event. I already mentioned it, and it's a nearby spiral galaxy, and you can see a nice image of the galaxy, a classical spiral, and you can very precisely pinpoint where in this galaxy the source is situated, and it seems that this region is related to star formation. So it goes well with hypothesis that FRBs are due to young neutron stars. Of course, it was interesting to monitor the Virgo cluster because in the framework of several hypotheses, we could expect enhanced rate of FRBs from this direction. And despite relatively long monitoring, people found nothing. It was done by a SCAP. Actually, they detected one FRB, but its dispersion measure does not correspond to the distance to the Virgo cluster. And so it looks like it's just a random background event, and there was nothing detected from the Virgo cluster. It puts important limits on models which link FRBs with extragalactic but relatively nearby population of sources. Rates are continuously re-estimated because more and more observations become available, and still surprisingly, the estimate made using just a single event made by Lorimer and co-authors in 2007 is still valid. So the initial estimate was like few thousand events per day. Of course, this number depends on the limiting flux, on the sensitivity of the instrument. But if we are speaking, for example, about Parkes telescope or similar instruments, then the limit is several thousand events per day. However, even for bright events, the rate is large, so there might be hundreds events per day with fluxes above 1 Jansky. So the latest discussion of the rate was given this month, and you see the reference to the paper. Especially the left plot is interesting because people compare the rate with the rate of different astrophysical transients like neutron star mergers, black hole mergers, tidal disruption events, and so on. And we see that the rate of FRBs is compatible with the rate of some supernova. However, we know that they're not linked, so we don't see any supernova events simultaneous to FRBs, and it coincides with the rate of white dwarf coalescence, more or less. Again, typically it might provide the supernova 1A if the resulting white dwarf is supercritical, so it's not very, say, interesting, but it's compatible with the rate of magnetar flares of soft gamma ray burst repeaters, SGRs, marked here, and this is one of the leading hypotheses at the moment. What else observations give us? Polarization. For several sources, now the number is about 1 dozen. Polarization was measured. That's the first example. So it was done less than 5 years ago. And in the first detection, they got linear polarization. Sorry, wrong button. They got linear polarization. Then for several sources, people measured circular polarization. And as I said, the total number of sources with known polarization is about 1 dozen. Okay, so let's come to the list of hypotheses. Initially, the situation was very interesting, and it was like with ultra high energy cosmic rays a few decades ago, when the number of hypotheses of about the origin of these particles was larger than the number of detected particles. So for the first several years, we were dealing with like 20 main hypotheses, really main without variants, without subdivisions. And there were just 10, 15 events known. Roughly, you can divide all these hypotheses into two large groups, neutron stars and different exotics. Exotics include something really exotic like cosmic strings, axion clouds, white holes, and so on. And of course, aliens, definitely. Neutron stars are somehow better because at first we know that fractions of millisecond is a good time scale for neutron stars. Then we know that they are sources of relatively strong radio bursts. So you just need to fit something to shake the magnetosphere maybe in some drastic way, but without destroying the source if you want to obtain repeating sources. And you produce a short radio flare, so it looked like neutron stars are very well fitted to explain fast radio bursts. At first, I'll mention two hypotheses which were quite popular for a few years, but now they are not considered as a possible explanation for the whole population. The first one is related to coalescence of neutron stars. It's even surprising that people did not predict very short radio transients. People discussed a lot long radio transients from coalescing neutron stars, and here are the list of authors. But the idea that they can produce very short bursts was put forward by Tatani only after, even not after the first paper about FRBs, but after the paper by Thornton and his co-authors. Now we know that the coalescence rate is not high enough to explain the whole population, and we don't see any coincidence between short gamma ray bursts and FRBs. The second idea was related to so-called supramassive neutron star. So typically Microsoft Office always underline and say you wanted to say supermassive neutron stars. No, supramassive neutron stars. These are interesting objects. They are newborn neutron stars, which are heavy enough. They might collapse to a black hole, but they are stabilized by rotation. So as they slow down, they collapse. So these are supermassive neutron stars. And if you have a collapse of such an object, of course, it's a big stress for the magnetosphere, and you can expect a short radio flare. Still now we know that it's not a good possibility because detailed modeling showed that the interval between the formation of a neutron star, say between a supernova or a short gamma ray burst or something like that, so the interval between this event and collapse cannot be very long. So we might see correlation in time between FRBs and other transients, and we don't see it. And of course, the rate is uncertain. There are many uncertainties in this model. Still, I want to say that even having many tens of models which are shown to be wrong in application to FRBs, we can consider many of them as predictions for some maybe more rare or more weak radio transients. So many of them are worth studying, but not in relation to fast radio bursts. Okay, so I'll summarize the situation with early ideas. So there were some real exotics like strings, axions, white holes, and we can say that this is completely closed. Then there are some catastrophic events like supernova, gamma ray bursts, and coalescence. They are more or less closed, at least if we try to explain the whole population of FRBs by a single mechanism. Then people discussed many ideas related to neutron stars plus something else, for example, asteroids falling on a neutron star. Again, this is more or less closed. It cannot explain all sources, but why not? Maybe it can explain some of them. So there are just two mainstream approaches at the moment. These are magnetars and pulsars. So the difference is that in magnetars, we emit the energy of magnetic field, so the energy of electric current, say. And in pulsars, we emit the rotational energy. So these are completely different mechanisms and are related to more or less different type of neutron stars. So the magnetar model was proposed immediately after the first event was reported in 2007. And later on, after the paper by Thornton, which really pushed the field, people started to develop it, and Yuri Lubarsky in 2014 proposed the first successful, I would say, reasonable model for the magnetar mechanism. Because in the first paper, it was just shown that from the point of view of energetics, rate, time scale, limits on counterparts, and so on, magnetar bursts are good candidates for explanation of FRBs, but no exact detailed mechanism of the radio emission was proposed, and in the paper by Lubarsky it was done for the first time. So the idea is that you have a giant flare of a magnetar, and the magnetar is surrounded by a nebula. And this magnetic pulse propagates, it starts to interact with the nebula, and so it sets on a coherent maser emission, which has maximum in radio, and so you can obtain a very short, due to gamma factor, due to relativistic effect, very short radio burst. Indeed, we know that some known magnetars are surrounded by nebula. Some are, some are not. And it's also important, so it doesn't mean that any magnetar might be a source of fast radio burst, because one of the main argument against this approach, against the whole branch, I would say, is that people tried to identify radio emission from giant flares of galactic magnetars, and there was nothing. And it's not even the question that no telescope was pointing towards the source, even with even not with the main beam of a radio telescope, you might see a flash because the source might be powerful and is nearby. But all these magnetars in our galaxy, which showed giant flares, they're not surrounded by nebula. Maybe that's the reason why they don't produce any FRBs. If we speak about non-magnetars, then quite recently people reported a radio burst which looks very much like a scaled version of an FRB from one of galactic magnetar. And it is, of course, not a very direct argument in favor of the magnetar hypothesis. Sometimes people want more, and especially for very active repeating sources, people discuss so-called young millisecond magnetars, when actually you take both huge magnetic field and rapid rotation. So it gives you an opportunity to release a lot of energy in relatively short time. So it means not in a single burst, but in a period of activity, because if you try to estimate how much the repeating source emits, then you count really huge numbers, and you need something like a young millisecond magnetar to explain the whole energy budget of this object. In my opinion, a major step in making theoretical models of fast radio bursts in the magnetar framework was made last August by Andrei Beloborodov, who published a paper in which he explained, I would say, all main features of FRBs in a single model, and there are interesting predictions how bursts are made in the wind outflowing from a magnetar. So more or less it lies on the same line as the original Lubarsky model, but is more advanced. And this area is intensively developed by several theorists in different countries. Okay, I'll keep it. this is just a set of equations from the paper by Andrei, and it's visible that, for example, typical peak frequency is of the order of what we expect, what we observe from fast radio bursts. Time scale is also all right. Luminosity, so all main parameters can be explained in a real physical model with a relatively detailed mechanism of emission. Now I want briefly to comment on the second mainstream model. So still people consider the possibility that sources of FRBs can be like radio pulsars. And the first idea was quite simple. It was mentioned already in 2007 in the same paper in which the Magnetar model was proposed. So the idea is very simple. We know giant flares from giant pulses from the Crab pulsar, and we can just scale it. Let us say that the energy of a giant pulse is scaled with the rate of rotational energy losses by a neutron star. So if we take a radio pulsar with a period not 33 milliseconds like Crab, but 1, say, millisecond, and slightly larger magnetic field, really less than the order of magnitude is enough, then you obtain an energy of such scaled giant pulse comparable with the energy of FRB if it is not at 1 gigaparsec but at 100 megaparsec distance. So it is possible to make them extragalactic just by scaling these giant pulses, and people try to develop this approach to a real mechanism. So the first step can be really simple. You just scale it. You say that the luminosity of the fast radio burst in radio is related to total energy losses, and you have some coefficient of efficiency, and you can obtain necessary numbers if you put this coefficient just to 0.01, so 1% of energy goes to the radio band. So at first glance it looks all right, but if you go deeper then it's not so, and I'll comment on it later. Then there are some predictions. To produce such giant pulses we need young pulsars. They might be situated in young dense supernova remnants, in dense shells of matter, and we can estimate the value of the dispersion measure simply due to this local media, and it can explain properties of FRBs, so we can put them at relatively close comparing with cosmological scales distance, and explain dispersion measure not by intergalactic medium but by surroundings of the source. But of course such a remnant is expanding, and there are clear predictions that dispersion measure will go down on time scale of, say, few tens of years, and maybe even now for the repeating source we can say that we don't see any changes in the dispersion measure, which somehow goes against this hypothesis. The burst rate can be all right in the model of radio pulsars, but again I underline if we speak about smaller distances, and that's the main problem, I would say, for this type of hypothesis. So to obtain large luminosities, if we want to go further, we need efficiency which goes close to 1, which is too much, of course. It's very difficult to imagine a mechanism of emission which puts all energy of the transient just in radio waves. And the second constraint, as I said, comes from expectations about the about evolution of the dispersion measure, which is not visible yet. So if we compare these two approaches, magnetars and pulsars, then they have some advantages and disadvantages. It's important that both of them don't predict any counterparts, but of course in the case of radio pulsars there'll be really no counterparts. In the case of magnetars there might be giant flares, simply we cannot see them from 1 gigaparsec or even 100 megaparsec distance. So in principle, we expect some counterparts in high energy, which are simultaneous with fast radio bursts, but we need much better sensitivity. And I'll say that now, basing on advanced theoretical analysis, we can say that for magnetars, there are just very few problems. For example, it's a problem to obtain nearly 100 polarization. But for pulsars, for which polarization, by the way, is not a big problem, there are many other issues, and it looks like the magnetar approach is winning up to now. Of course, the direct proof would be detection of spin period and maybe period derivative. If we're dealing with neutron stars, at some point we might obtain it. Sources in both approaches, they can be related to not so old supernova. So maybe in a few years of observations now we have several very effective supernova factories which provides lots of events. So even if sources become active as FRB sources, say 10 years after a supernova, then very soon we might see some coincidence. And of course, the best thing would be to find counterparts. I just remind that the puzzle of cosmic gamma ray bursts was solved by detection of counterparts. So the current rating of hypothesis is like this. There are two main approaches, and the magnetar one is somehow winning. And I have to come to the end. I'll skip usage of FRBs for fundamental physics, but people try to use it to test equivalence principle. If we observe counterparts, also it would be possible to probe Lorentz invariance. People use sources with known distances to put limits on the mass of photon, and that's quite a recent result from last July. And I'll finish with a very brief list of observational facilities. So many radio telescopes now have equipment which allows them to detect and identify such short, non-repeating radio bursts. And new systems appear. So Aperitif just recently started to work on FRBs, and already they demonstrate some results. So last December they reported their first detections of the main repeater of FRB 121102. So everything is working well there. People installed a new system of transit identification on the VLA. It's not the best instrument to search for FRBs because of very tiny field of view, but still it can be useful maybe together with other instruments when they monitor repeating sources, for example. The 500-meter telescope in China is working on FRBs. They understand that they are better than Arecibo also for this type of sources, and they also reported their first tests. So people really use this FRB 121102 as a test bed for systems working on these radiotransients. And of course, everybody's waiting for SK. They will have a huge rate of discovery, but I would not bet, but I believe that will solve the puzzle before SK is fully operational. Um, One of the main topics is to find counterparts, and people are developing different programs, often not especially for FRBs, but there are effective teams of observers working on counterparts of gravitational wave events, and also they can use other triggers, and FRB is one of them. So maybe these systems will provide new data and identify the first counterparts outside the radio band. And as the final slide, I want to show this one. It's a recent preprint about a very simple and very cheap installation. There are two in states. So the idea is to make 4 very cheap stations, significantly separate from one another. They can detect only very bright sources. They don't measure positions, but as far as they are separated, if they obtain simultaneous detection, then altogether they can identify the FRB. Because they are installed in different sites, then RFI is different for them. And so it's an example of a very cheap system which can obtain some interesting results in this field. Of course, unfortunately, they can see only bright bursts, so the number of detections will be very small for them, but they already installed 2 stations, and the system will become fully operational soon, I hope. Okay, so that's my summary. The field is rapidly developing, and any review is, I would say, old today, but still there are several main reviews. You can find them in the archive. So in the catalog now, as I said, there are 110 bursts. There are 20 repeating sources. 4 sources are well localized. For 13 sources, we have polarization data. For 9 sources, rotation measure is measured. Some of FRBs are very bright, so the record flux is more than 100 Jansky. Dispersion measure covers a very wide range from 2,600 down to 100 roughly. And mainly sources are detected at nearly at 1 gigahertz, but now there are several significant detections at 600 and also 400 megahertz with CHIME, and there are claims for several detections at even lower frequency at Pushchina, but this I put with a question mark. Okay, I'll stop here. Thank you.